Hello, I've got 5 predator-prey system questions to go over for MA303's Exam 1. These questions have been taken from 3 different types of resources from summer 2019, both Exam 1, the practice set for Exam 1 posted by Dr. Chen last summer, and I believe Quiz 3 from that same semester. So I've kind of tried to order it from easiest to hardest as far as the questions go. So we're starting off with one that's just about phase plane reading. So we have a system of differential equations used to model the competition between two species, and the direction field is shown below. What is the behavior of the solution with the initial condition 1, 1? So let's find 1, 1, right about there. And what's going to happen? Well, what's going to happen is exactly what you think is going to happen. We just follow the direction lines. And that leads us to what looks to be an improper nodal sink right there. And so, yeah, we're going to get stuck here. This is a sink point. So as time approaches infinity, any points that that start in this point zone of control anywhere near it, and in fact, unless there are any critical points that we can't see up in these directions, everything over here is going to get pulled into this point eventually as time approaches infinity. So yeah, we're just going to get stuck there. And what does that mean for our system? Well, at t is equal to infinity, our x population is 4 and our y population is 6. So our system has reached some kind of coexistence where we found a ratio that works between our predator and prey, such that the prey is their population is growing at the same rate that they're being eaten by the predator, and that's enough food for the predators so that their population also remains stable. So yes, we have answer choice D. A is very close. The species coexist and the system has cyclic periodic behavior, but that would be the case if we had a center here. If we had a center, then you might expect our solution curve to curve in a little bit, but then to enter some kind of stable orbit, which we do not see here. Now, looking at these other ones, if X was to become extinct but Y survives, then we would expect some solution here on the Y-axis, and likewise for option B, for C, if Y becomes extinct but X survives, we would expect some solution along the x-axis. And of course, both species going extinct would mean starting at the point 0, 0. Because that's a source point, if you start anywhere away from it, away from 0, 0, you're going to get pushed away, and you're never going to make it back there. So no matter what, for this system, both species will not go extinct. Question 12, what kind of system is this in terms of the behavior of the predator and prey that the system represents? So these can often be the hardest questions to really wrap your head around from this topic, but if you break it down, it becomes a little bit easier. So let's think about what happens to each one of these populations, our population of X and our population of Y, with the absence of the other population. So let's kind of decouple this system. Let's take our population X and just put it in a different part of the forest or something from the population Y. So in the X world, there are no more Y's. Y is equal to 0, and in the Y world, all of the X's are equal to 0. So what do our equations become? We have dx dt is equal to, well, we have no y's in our x system anymore, so we have negative 4x. And then what about our y's? dy dt is equal to negative 3y. And probably just from these, you can tell what's going on here. We're going to have exponentially decreasing populations of x and y, and we can actually just solve these equations, and you will get an e to the something term as x of t. But I'm a little lazy. I'm not going to do that. That's a MA266 topic. But you can go and do that if you really feel like it. But yeah, okay. So that's what we get. We're getting exponentially decreasing populations in the absence of the other population. What if we start adding y's back into the x system? Is that going to increase dx dt or decrease dx dt? Because remember, dx dt is the change of the population over time. So if we add some y's, this 2xy term is going to be positive because there's no way that this x term can be negative. All of our populations have to be greater than 0. So necessarily, adding populations of y into our system of x is going to increase our population because it will increase dx dt. So for every unit time, we're going to gain more, or at least lose fewer members of the population x. And similarly, for y, if we add x's to this system, we will increase dy dt because this term is positive. Yeah, and so that should help us answer everything down here, because what we can say is that because both of these interaction terms are positive, the terms that include x and y multiplied together, we can say that that system isn't in competition. They're actually helping each other out. So having more y's is good for x, and having more x's is good for y, and so we call that cooperation. So what do we have? Yeah, we have D, exponentially declining populations. That's just from our negative 4x and negative 3y, and cooperation. That comes from our interaction term. Okay, then one other note, a logistic here, that adjective comes up, logistic growth or decay comes up when we have, let's say this was x squared and y squared. That would be logistic decay of both of these populations. Okay, but that's it for this one. Let's go look at one of the quizzes. I lied, this isn't a quiz, but this is the one that we're going to do now. A system of two competing species whose populations are denoted by x and y are represented here. Neither of the two populations is 0 initially. Which of the following statements is true? And interestingly, two of these statements are actually true, and it's a really niche case, but you'll see how this works out in the end. So let's express these. Well, no, we're not going to express these as matrices, but let's rewrite these equations and try to find our critical points. So we have x prime is equal to x times 1 minus x minus y, and y prime is equal to y times 1/2 minus 1/4 y minus 3/4 x. Looking a little crazy at this point, but since everything is multiplied by either y or x, what do we know? Well, that means that our system is homogeneous. We have no constant terms, because even though we have some constants in here, they're really multiplied by the variables that we have outside here. So we know that 0, 0 must be a solution, and so that is one of our critical points. What if y is equal to 0? Well, if y is equal to 0, then this equation is taken care of. X can be equal to anything because we're multiplying y by everything. This equation will always be 0. So if y is equal to 0, what we're left with is x prime equals x times 1 minus x. And what does this give us? This tells us that if y is 0, either x can be 0 or x can be 1. So that gives us a new critical point of 1, 0. Now let's do the same thing for x. What if x is equal to 0? Well, this equation will automatically be 0. Y can be anything. And we'll take this equation and rewrite it with x is equal to 0 as y times 1/2 minus 1/4 y. So this says y can be 0, or y can be 1/2 is equal to 1/4 y multiplied by 4, y is equal to 2. So that gives us 0, 2 as another critical point. And now our last critical point will occur, assuming there is one, when x and y are both not equal to 0. Well, when that's true, what can we do here? And I really should have done this earlier. Replace these with zeros, because that's really what we're solving for. Well, if x and y are not equal to 0, then we can legally divide both sides by x over here and both sides by y over here. Because, otherwise, if we have 0 over 0, that causes some problems. So we can divide out that x, divide out that y, and then let's rearrange this equation right here, move a y over. We see that y is equal to 1 minus x. And if y is equal to 1 minus x, we can substitute that in here. We have 0 is equal to 1/2 minus 1/4 times 1 minus x minus 3/4 x. I don't like dealing with all of these fractions. Let's multiply both sides by 4. That gives us 2 here, 1 here, and minus 3 here. And so what do we have? We have 2 minus 1 plus x minus 3x. That gives us minus 2x here and 1. So 2x is equal to 1, or x is equal to 1/2. And since y is equal to 1 minus x, y is also equal to 1/2. That gives us a point of 1/2, 1/2. Great. I'm going to get rid of this. This isn't really useful work for us because what we need to do right now is to linearize the system, to figure out what all of these critical points are, what their behavior is in this almost linear system. So to do that, we need the Jacobian of xy, assuming that we call this equation up here f, and this guy g. What we can do is find our Jacobian, which is the partial derivative of f with respect to x, fy, gx, gy, like that, just using all those partial derivatives. Now finding those, what will be the derivative of f with respect to x? Well, actually, let's rewrite these. F is x minus x squared minus xy. So that will give us 1 minus 2x minus y. If we take our derivative with respect to x, what about y? We'll get negative x. Now for this guy right here, this is g is equal to 1/2 y minus 1/4 y squared minus 3/4 xy. So our derivative with respect to x will give us minus 3/4 y, and with respect to y will give us 1/2 minus 1/8 y. Minus 1/2 y minus 3/4 x. Okay, still looking kind of crazy, but this is our Jacobian matrix here. So let's plug in our points. So the Jacobian at 0, 0, our first critical point, will give us 1, 0, 0, 1/2. And because this is an upper triangular matrix with 2 positive eigenvalues, we know this will be an improper nodal source. Right there. What about our Jacobian of our next critical point, 1, 0? What will that give us? That will give us 1 minus 2, so negative 1 here, negative 1 here, 0, and 1/2 minus 3/4 will give us negative 1/4. Again, since this is an upper triangular matrix with two negative eigenvalues, let's make sure that is correct, right? Let's make sure that critical point works to begin with. I'm second guessing myself. 1 times 1 minus 1. Yep, that works. And then, yeah, okay, it does work as a critical point. Fine, great. So this means since we have 2 negative real eigenvalues that are not equal, we have an improper nodal sink at 1, 0. What about the Jacobian of 0, 2? I know this is tiring. This is not very fun for me either. We have negative 1 here, 0, minus 3/2, and what about over here? 1/2 minus 1 is negative 1/2. Again, 2 negative real unequal eigenvalues gives us an improper nodal sink. And this is a bottom triangular matrix, but we can, lower triangular matrix, but we can still just extract these eigenvalues from the main diagonal, and you can solve directly for that and find that as well. Now finally, the Jacobian of 1/2, 1/2, what will that give us? Okay, that will give us 1 minus 1 minus 1/2, then minus 1/2, 3, so -3/8 there. I don't like this at all. And 1/2 minus 1/2 minus 1/4 minus 3/8. Great. So that's 4/8 minus 2/8 minus 3/8, which is -1/8. Great. Awesome. What we should be able to do is multiply this entire matrix by a factor, and it'll still have the same behavior. So let's multiply it by 8. We get -1, -3, -4, and -4. So we'll need to actually solve for the eigenvalues of this on our own. It's not a triangular matrix, so we don't have an easy way out at this point. So we're solving, of course, the determinant of a minus lambda I equals 0. That will expand down to -4 minus lambda times -1 minus lambda minus 12 equals 0, which is lambda squared plus 5 lambda minus 8 is equal to 0. That is -5/2 plus or minus the square root of 25 plus 32, so 57/2. Okay, so the square root of 57 is between 7 and 8. Divide that by 2. That's greater than -5. That's greater than 5/2. So this will give us, if these are our lambdas, this will give us one positive eigenvalue and one negative eigenvalue, and they're both real. So that means that this is a saddle point. Okay, at this point, we're ready to actually write a solution down. So which one here do they say is the correct answer? Well, they say that one species may eventually die out and the other one will survive. And really, before I selected that answer, I should have actually graphed what we're dealing with here. And we only need the positive, the first quadrant here. So at 0, 0, we have an improper nodal source. So things around 0, 0 are going to be attracted. Source. It's a source. So things are going to be repelled away from 0, 0. At 1, 0 and 0, 2, we have improper nodal sinks. So 1, 0, so this is 0, 0. At 1, 0, things are attracted in the general vicinity. At 0, 2, and this is not drawn to scale, 0, 2, we also have an improper nodal source. So things will be attracted there. Then what about 1/2, 1/2? That'll be right around here. 1/2, 1/2. That is a saddle point. So while some things will be pulled in, eventually everything will get pushed away from 1/2, 1/2. So I'll just write it as a completely repulsive point there. Okay, so if we have a system that starts out with neither of its populations being equal to 0 initially, what we would expect is for them to eventually, over time, reach one of the asymptotically stable points, which is either 0, 2 or 1, 0. The thing is, that is not the only answer. And you can see if we erase that, yeah, they say the answer is E. What if our initial condition happened to be 1/2, 1/2? Well, we know at 1/2, 1/2, dx dt and dy dt are equal to 0. So if you start exactly on that saddle point, you're not going to go anywhere. And so one other technically correct answer is both species may coexist in a stable way. But this is the much more obvious answer, and it's, I don't know, but it's good to recognize that C would also be correct in a little bit of a roundabout way. Okay, this problem was really grueling. Didn't really like it, but whatever. Let's move on to our quiz questions. Question 1, find out the critical point of the almost linear system and determine its type and stability. So we should only be getting one critical point for this system, and you can see that right off the bat because this is just a linear system with some constants added, so all that's going to do is shift where our critical point is away from 0, 0, which is where the critical point of a linear system always is, but it's not going to change the behavior of it at all, so this is still almost linear. Okay, so in order to solve for this, we set dx dt and dy dt equal to 0. So 0 is equal to x minus 2y minus 8, and 0 is equal to x plus 4y plus 10. Now I'm going to rewrite equation 1. 2y is equal to x minus 8, and we're going to substitute that into our second equation. So we'll get 0 is equal to x plus 2x minus 16 plus 10, or 0 is equal to 3x minus 6, x is equal to 2. And since we know this, since we know that this works, this relation between x and y is valid, then we can say that 2y is equal to negative 6, or y is equal to negative 3. So 2, negative 3 is our critical point. Now, in order to determine the type and stability of the critical point, we'll have to linearize our system. So we'll call this F, and we'll call this guy G, and we'll use our Jacobian matrix, whose formula is Fx, Gx, Fy, Gy. And in our case, because this is just a very simple, almost linear system with only some constants added, it's gonna work out really nicely. Because the partial derivative of f with respect to x is 1, then we have negative 2 and 1, 4. So it's like we took this system and just got rid of the 8 and the 10, because if we set up x prime equals this times x, we get exactly those equations without the constants up there. So let's find our eigenvalues, and then we will be done. We have 1 minus lambda times 4 minus lambda plus 2 is equal to 0. Lambda squared minus 5 lambda plus 6 is equal to 0. Lambda minus 2 times lambda minus 3 is equal to 0. So lambda is equal to 2 and 3. That means that this point here, this point is a improper nodal source. And it is unstable, like all source points are going to be. Yeah, that's about it here. Question 2, consider this predator-prey system. Use the Jacobian matrix to derive its linearizations at its 2 critical points. So we're not actually doing any analysis of this predator-prey system here. And, oh, I just realized, sorry, this is the predator-prey video, is it not? Yeah, this question was completely irrelevant. Well, okay, sorry about that. I guess you got a little bit more practice. Whoops. Let's use the Jacobian matrix to derive its linearizations at its 2 critical points. And this one might as well also not be a predator-prey system. They're not actually asking us to talk about what's going on in the system at all. So instead of actually doing any linearization, because we know how to do that, we just did some extra linearization a second ago, let's talk about what this predator-prey system is actually doing here. So if we do what we did earlier and rewrite these equations, but with the x population kind of segmented away from the y population and the y population also away from all the x's, what will we get? Well, in the absence of the y's, we get dx dt is equal to 200x. And dy dt is equal to negative 150 y. So what does this mean? This means that x is growing exponentially, and y is decaying exponentially. And remember, if we had any squares or cubes in here, then that would be logistic growth or logistic decay. Now, what if we start adding back in the other population, the one that we took out from each equation? So if we start adding back in y's to the x system, it's going to decrease dx dt. And what does that mean? Well, if we kind of picture this thing happening in our head, the y's are eating the x's. The more y's that we put into the system, the fewer x's we get in the population because they're being eaten. So that means that y is the predator and x is the prey. And that makes kind of intuitive sense with what's going on with these simplified equations in the absence of the other population. If there aren't any predators, the prey populations are going to go out of control. If there are no prey, the predator populations have nothing to eat, so they will die out. And finally, the only last thing to note is that dy dt really does act like, y acts like a predator because it has a positive interaction term. So any additions of x into the system will increase the growth rate of the population y because it's just more food for them to eat. Okay, so hopefully that gives you a little bit of a stronger grasp on what's going on with these predator-prey systems and gives you a little bit more of an intuition to help you during your exam, assuming this comes up. Okay, yeah, see ya.